I'm just gonna start it recording and take it away.
Okay, thanks a lot, John, and hi, everyone. So I was told that the majority, I think all of you folks are writing some software, I think specifically for variational algorithms. So that's very exciting, and I'd love to hear more. But so I thought I could speak a little bit towards that about just some good practices in building quantum software. And the case study that I'll use is a piece of software that we have for doing error mitigation. So I'll speak a little bit about that too. And then just to start off with, I'll say a few words about my background. And if there's any questions, I don't know what the standard procedure is, but just feel free to interrupt me if you can, or write something in the chat, and I'll do my best to keep an eye on that. So for the background, yeah, as Joan mentioned, I've worked in quantum algorithms, variational algorithms, and non-variational algorithms, and then error mitigation. That's been like the bulk of my work. So that's the outline in red and the majority of what I'll speak about. And then there's some other various work that I've done in the lower two boxes. I won't speak too much about that today, but just if you're interested and want to ask about it, that's there. The guiding question for me is always, can we use quantum computers for scientifically interesting and useful calculations? So that's the main thread that goes through everything. For the variational algorithms, there's sort of three main works that I've outlined here. And I guess you folks know these pretty well now, but they all have this similar flavor where you're using the quantum computer to prepare this state, this variational state, which in some sense, at least you hope, is hard to do classically. And then you have this optimization routine to usually minimize an energy, or depending on the application, it could be something else. So in the top left, there's the one for compiling. So there, the thing you're minimizing is like how far away you are from a target unitary. And in the top right, what's this one? I forget. I think this is variational state diagonalization. So that's like how your cost function is how diagonal are you.
Ryan, how could you forget? That one's the one we did together.
Yeah, I know. I should. All the diagrams are so similar. We made them.
Also, for context, one of my top students who's in the room is working on your linear solver algorithm. That's Indy. Indy, say hi.
Hi.
Great. Hi, Indy. Yeah, so you know the bottom one. So this one, the cost function, is like how solved is your linear system of equations for some definition of that. And again, you're preparing the solution to this on a quantum computer, and you're computing the cost of it that way. Okay, so that's a little bit of the spirits of variational algorithms, which I think you folks know. And then the quantum error mitigation is, yeah, it's pretty basic. The idea is you want to run this on a quantum computer, and when you do that in practice, either now or in the near future, whatever the near future means, then there, it's not going to be super great in practice. And so there's a lot of ideas for helping this. The main one is error correction, and then like error mitigation is anything that helps that's not explicitly error correction, is like the usual definition for it. So there's a lot of techniques, that other people have thought of and that we have thought of, and they're sort of all going into this software package, which we call Mitiq, which kind of looks like, mitigate, and then it has a Q in it. And so, yeah, the procedure of this is like, on the top right, you want to run some circuit that, you've either written in NISQ, which is Google's thing, or Qiskit, IBM's thing, etc. And you have some hardware that you want to run it on. So Mitiq, and I'll explain this more in a minute, but Mitiq is like, it sits in the middle. and it's this sort of intermediate compilation layer. You can think of it that way, which takes the circuit that you want to run, does something to it, according to some error mitigation technique, and I'll explain two of them and how we built the software, based on them. So maybe that will, be enlightening or insightful for you folks, and then gives you the output result that you care about. So yeah, there's a archive paper now in Quantum, I think. So that's the one on the top left. The downloads is quite dated now. I think it's up to like nearly 100,000 downloads, which is cool to see. People are using this and getting use out of it. And then we've done stuff like try it on AWS's quantum computers and see how it performs there. I should say try it on AWS Broadcat, the platform, and the actual computer that we used is the Rigetti device there. So that's a technique here in the plot that's called ZNE, and I'll explain that later, but this is just a quick overview. In addition to us using it and folks downloading it from GitHub, PyPy, people are using it to do research, which is also cool to see. So just two quick examples. The top, some folks at Perimeter used it to study the real-time dynamics of plaquette models on NISQ hardware. And the circuit that they're using on the right, they say somewhere, using the Mitiq package for folding a circuit. So that's using the ZNE technique that I mentioned. And then at the bottom, slide's a little dated also. This is not in preparation anymore. It's on the archive, but we used this to do some novel experiments where we show you can increase the effective quantum volume of here to IBM computers. So if there's questions about this, feel free to ask. I won't say too much about it now, other than the higher you are on this plot is better. And the blue one is using error mitigation, and the orange one is not using error mitigation. So the blue points are higher, and we show that we're able to increase the quantum volume on these plots. Okay, and just very quickly, this one is not in Mitiq yet, but just still in the prior work section. We've also developed some new techniques, or maybe framework is a better word for doing error mitigation here. So this one we call logical shadow tomography, also published now. Slide is old. And here the idea is you perform shadow tomography, which is a sort of sample efficient technique for doing tomography, and consists of measuring in random bases, which are the UI here in this middle panel. And you do that on a encoded or logical state. So it's like a sort of baby step towards error correction. You do the encoding part, but not the full syndrome measurement and correction. But if you do this procedure, then we show that you can compute basically two quantities of interest. And when you take the ratio of these two, you get an output that's closer to the value that you would have without noise than if you didn't use this procedure. So those are the sort of two plots at the bottom. The left is using a 513 code, and so sort of simple experiment there. And then on the right is just showing the convergence in the number of samples, which is in contrast to other methods for doing these techniques. Samples is the sort of the main resource overhead that we have.
Yes.
Okay, so that's the background section. Were there any questions on this before I move into the software part?
I think I want to talk a little bit about how it applies, like how I would be able to use this for VQLS, but I think like after when you're done your presentation, I can ask more specific questions.
Okay, I'll keep that in mind, and we'll see some examples, but yeah, let's come back to that.
I have a kind of silly question. Why is the fidelity greater than 1 on the y-axis?
Yeah, good question. So it's not showing the variance, but because you're estimating the quantity, Even though, yeah, physically, it shouldn't be above 1, it's an estimate, and the estimate's not necessarily physical. The important thing is as you converge, you do converge to a fidelity of 1. But that's a great point. Yeah, because you're estimating it, it can be non-physical. Yeah.
Oh, interesting. I didn't know that. So this would be like these are experimental results, but it's not a simulation, or like where does the data come from?
I didn't fully hear that. Can you repeat? Sorry.
Sorry, I'm just curious where the plot comes from. Like, is this experimental data from a quantum device, or is it a simulation?
I'm still not able to pick that up.
Sean, your microphone quality, I think, would you be able to switch to like another microphone maybe?
Or type it out.
Or
maybe put it in the chat too.
Yeah. We had this issue before. If you just try speaking closer to your mic. I think last time was a little bit better. Maybe chat is just better.
Yeah, sorry.
No problem. Let's see if I can find the chat. Yeah.
They might be it might take them some time to finish typing out what they want, but
okay, I have it open, and if it pops up, I'll come to it. But by the way, can you see the chat on my screen?
No, we can't.
Okay, good. Zoom makes sense then. Okay, so good. So let's now move into okay, here's your formal definition of quantum error mitigation, coming with a meme. So yeah, you want to prepare the state psi, but the best you get is psi passed through this noisy channel, which is the script E here. And another way to say that is, normally especially in these variational algorithms, we want to compute expectation values, which is to say you have some observable O, a state psi, and so you want this overlap here. But in reality, the thing that you get is, again, the state psi replaced with psi passed through this channel. So, and then, that's you could also assume the channel acts on the observable here. And that's, of course, valid and closer to what happens experimentally. But here I've just written it as the perfect observable. So the idea of error mitigation is that let's take what we can compute. So what we can compute is exactly the reality, the thing that happens in the experiment. And but we can't prepare the state psi perfectly, but we can prepare a series of states, a family of states, psi j. And then you can also think about, we can sort of do something to adjust the noise in the device. So it may look weird here to parameterize the channel, but this will be motivated in the first example that I show, zero noise extrapolation. And then once you have this, then you can sort of try to take a linear combination or a nonlinear combination or whatever. Here's the linear combination with some coefficients Cij. And maybe these are something that you have to learn, or maybe these are just sort of, you compute them based on the technique that you're doing. And then this is your final output. And you hope that this is closer to the real value, to the expectation than would have been otherwise. And I say hope, that means like you design the technique such that this should work, with some confidence level or something like this. Okay, so that's error mitigation. And again, yeah, like it's super general, whatever fits into this works. In some sense, you could write error correction in the scheme, but just like colloquially, we think of error mitigation as lower overhead than error correction. So here's the software. And to introduce the software, this is the typical workflow that you have in an experiment. So I mentioned this earlier, like you've written something in Qiskit, or you've written something in Rigetti's Pikewell. So you have what we call a quantum program. And then there's some other hardware or simulator that you want to run on. And this could be, something in IBM's cloud. It could be a, simulated noisy device like you can do in Qtip or whatever. But you have like this sort of arrangement where you have a program, you want to run it on what we call a backend, so either hardware or simulator, and then you'll get out an expectation value. Not always an expectation value, but I'll just assume that because this is what most of the error mitigation techniques assume. It doesn't have to be all of them though. Okay, and then if you want to do error mitigation and you want to do that with software, then there should be this sort of middle layer, something that sits between you, the user, and the backend that you want to use, which sort of intercepts the program that you want to run and then does something to it, sends that to the backend, and then interprets the results or combines the results in the very analogous way to that I showed on the previous slide, and then gives you out the error mitigated expectation value. So that's a reasonable interface, and it's nice to have this because as I'm sure you folks are encountering, there's a lot of thought that goes into already creating a program, and maybe there's parameters and at some point you want to not have to do all of this sort of low level stuff yourself. It's nice to have software which can automate this, especially if you want to repeat it. And so that's some of the design principles around which we've built Mitiq. So it should be backend agnostic. So any hardware you want to use, it should accept that. And then in terms of the front ends, ideally it would be completely front end agnostic. Front end meaning like the program that you write the circuit in. And I think this will be the case in a few years, but right now everyone's still defining their own Python quantum circuit class, etc. And so it's not completely standardized yet, and I don't think it should be. But so here we wanted to support as many front ends as possible, and all the major ones we do. Yeah, okay, easy to use, that's always nice to have. And then it doesn't have to be completely black box in this way, especially since this is sort of a very active area of research. It's not like production level code. You want to get in and play with the lower level parameters yourself, especially if you want to use it to do research. So that was also a key design principle in Mitiq. And yeah, and I'll speak about sort of how we tried to achieve these, and speak about some particular examples. So the first example is zero noise extrapolation. So here's the big picture overview, and then I'll break down exactly what this means on the next slides. But here is just to emphasize that this and the next technique that I'll show you fit exactly into this framework. And this was because I guess one tip is try to think about how general your software should be, and how to design it so that it can certainly accommodate all the things that you want to do. And then another thing that we were very aware of could happen was new research comes out, and we need this software Mitiq to be able to be adapted to that. And so that was also a key design principle. But for ZNE, this was published before by the IBM group. And here you modify the program by creating a set of what we call noise scaled programs. All of these, some number of them, are run on the back end. And then the expectation values that you get, you sort of do a linear fit to them, and then you extrapolate to the zero noise level. So hence the name. So that's one technique. I'll go more in detail about that. The other technique, also from the IBM group, probabilistic error cancellation, or PEC. Similar workflow, and it fits exactly into the package. And here you're doing a little bit something different. You're not exactly scaling the noise, but you're sampling in a way that I'll define later, but you still end up with a set of programs that you need to run. And then after you run those, you have a set of expectation values that you need to put back together. And so it fits into this framework too. Was there a question that I heard, or are there any questions at this point?
I think I just wanted to ask, does ZN, like I think recently IBM like maybe put out something that was like, oh, we need to do something useful with quantum computers, and I think they were pointing to like simulations or something like that, something to enhance quantum theory, and that uses ZNE, right? Or am I wrong?
I think so. If we're thinking of the same recent paper, like the 127 qubit, yeah, they use ZNE.
Yeah, that one. Okay, good to know.
Yeah, absolutely. Yeah, great point. And yeah, so well, IBM, introduced it and uses it frequently, and other folks do too. The nice thing about it is it's very cheap in the sense that it doesn't take a lot of overhead to do, and we'll see that in the next slides. And it's also the technique that we use to, I mentioned at the start, to increase the quantum volume of a few computers. But yeah, good question. Let me go back to the chat to see if the one I couldn't hear was asked.
Sean, did you want to like type out your question that you had? Or
Sean rejoined on their phone, so they may be able to.
Okay. Okay, well, we can
I can save it for the end. It's not. I don't want to interrupt.
okay.
Okay, I think we can come back to that one then.
Yeah. So they
Okay.
said they'll ask their question at the end.
Okay, perfect. Great. If there's nothing else now, then yeah, let's get a little bit more into the details of at least one of these, and we'll see how we're doing on time. Okay, what am I saying here? So yeah, okay. So you don't need to know all of the things that I just showed or all of the things that I'm about to tell you. It's nice if you do, you can know what's going on, but you shouldn't have to, of course, if you want to use the software. There's a big big difference between the interface of software and the implementation of software. One of the most important things to keep in mind: interface meaning how does someone use it, implementation meaning what actually happens. So that's like behind the scenes in the yellow box there. You always run into trouble if you try to mix these two up, and it's very important to keep them separate from the start and throughout the design of good software. So that's the second tip that I can give you. So I think I mentioned most of these. So circuit, anything that you want. And then here's a slightly new thing. So I mentioned any backend that you want. What we require here and how we supported this, and this was a big design decision too. We sort of black boxed it in the sense that what we require is a function which inputs a program and then outputs an expectation value or something from which you can compute an expectation value. For example, like a bit string or a set of bit strings. So this was a thing that we discussed a lot, and I think we did it correctly. There's a lot of different ways that you could do this, and it can get very messy very quickly because of all the different interfaces for using different backends. It's very non-uniform, and it varies a lot by different qubits, etc. And so I think we made the right decision to just abstract all of that away and just say, you give us the function which takes this circuit and runs it and on whatever computer that you want to. And then once we have that, then we'll be able to use this function to do the error mitigation techniques that you want to do. So that was a big decision of Mitiq. And yeah, so once you have these two ingredients, if you've written your own software this way, or your own script, then the result that you would get is just calling execute on the circuit that you defined. And
Sorry, just a question.
yeah,
So this execute
please.
function, because I know like with VQAs, you have to do that like classical loop. So this is kind of before that optimization of the parameters.
Great question. There's no like super clear answer whether to do error mitigation during the optimization procedure or if you can get away with just doing it after. I can give you two examples. Like one, the first one, suppose the noise is so bad in your computer that the optimization landscape is just completely flat. And it killed, you know, the local minima, the global minima, whatever. And so in that case, you couldn't optimize anything. And so there you would probably have to use error mitigation while you were doing the parameter optimization. On the other hand, for a lot of the variational algorithms, you'll see the optimization landscape is affected, but the global minimum is like roughly sit in the same spots. And if that's the case, then you can say, okay, just get the parameters close enough, do the optimization without doing error mitigation. And then at the very end, I'll add on this error mitigation to improve the result that I have and maybe do a little bit more optimization, but it wouldn't be fully necessary. That's a great point though. Does that answer the question?
Definitely. Thank you.
Yeah. And so, yeah, at this point, there's no Mitiq. You would just call execute circuit. Now with Mitiq, the way we designed it is there's the sort of similar interface. So we have another execute function. And so it would be similar to your code, but here you pass in the circuit and then the thing that runs it on the hardware, the execute function, and then this will do all of the details of the technique. So the pattern that we went with is, you know, like execute with some technique, or also just like mitiq.zne.execute as an alias. But this is the interface that we chose to go with. And this is another, you know, big important decision when you're designing software is because this, you know, when you're seeing it for the first time, I think you folks are now, this is what you see. And if you want to go try to use the software, then this is the first thing that you try. And if it's super complicated and it involves you to do, or it makes you do all these steps just to fit into the framework and use it, then that's something that might turn you away from the software. But if it fits pretty well with what you already have and it's easy to add in, that's a motivating factor then. So you want your interface to be as close to that as possible. The 3 dots that I have are like more options that you could add into here, the ZNE technique or other techniques that you might want to use. As an example of another technique, there's the other one I mentioned, PEC. So you see the similarity. That's also an important thing in terms of the usage. Okay, that I can skip. So yeah, let's see a little bit more of a code example now, and then we'll get into what's going on under the hood. So you can import the ZNE module from Mitiq like this. Assuming that the user has already defined the circuit and the executor, the execute function, then you can run zero noise extrapolation with just this line of code or lines, whatever. So that's nice, this abstraction. And here's 2 examples of using it, which I haven't shown before. So 2 plots. On the left is an IBM computer. On the right is a Rigetti computer. I think now both are deceased, retired. They don't exist anymore. But you get here, yeah, you get a little bit of the idea of what happens with ZNE. So on the horizontal axis is what we call the noise scaling factor. So that's the lambda. And lambda I could range from like the smallest thing is 1, which means that it's just the base hardware noise in the computer. And you want to get to, you know, a noise scaling value of 0. You know, that would be great if you could just set it equal to be 0. Unfortunately, it's not that easy. But what you can do, the sort of clever thing is you can make it larger. So you could set lambda to be 3/2. for example. You could set lambda to be 2, so doubling the noise, for example, and so on. And then if you have some idea of what this behavior should be, sort of what this trend should be, and here we know that for the particular experiment we were doing, it should be like an exponential decay. It's just like a randomized benchmarking experiment. Then you can fit something to it, fit some model to it. And here in the purple is the exponential one. And you can see that the correct value, that the noiseless value that you should get in this experiment is 1. And the ZNE value, within the error bars is definitely better than the unmitigated value that you're getting. So that would be this one here. And this is averaged over like, I forget how many different circuits. But that's the idea of ZNE. Now there's a little bit of an art to it, like I said, because here for this experiment, like I mentioned, you would expect it to be exponential, and you do see that on the IBM device. On the Rigetti device, it's much less exponential, sort of almost linear. And here we actually see that, yeah, like a linear fit. Okay, linear is not too good here, but maybe like a quadratic fit is giving the closest value to the true answer, rather than the exponential one, which has a very high variance here. So it's a little bit of an art to use ZNE, but if you have a good noise model, good understanding of what your device does, and then you can tailor the lambda i's that you use and the extrapolation technique that you use, and you can get pretty good results in a very cheap way. So what does cheap mean? The number of resources that you need here is like, instead of just running one circuit, you would run one circuit per noise scaling value that you have, right? So there's this multiplicative overhead and the number of circuits, and then to do the fitting and the extrapolation, there's closed formulas for this in a lot of cases, and it's not hard to pass it into SciPy or something in general. And so this is easy. So that's why ZNE, you're not using any additional qubits, and you're not using too many extra gates. You're just sort of using a multiplicative factor of circuits, and then you can extrapolate to the zero noise result in that way. So that's mostly ZNE. Now, as I showed on the x-axis here, there's if you wanted to use this at a lower level, you might want to pick the noise scaling values that you use, and even not the noise scaling values, but the different techniques for scaling noise. So I have a slide on this in a second, which is easier to explain because it's visual. But for now, I'll just say there's different methods to scale the noise. And here we've selected one of them, which we call a global unitary folding. I'll explain that in a second. And then here's the one that has the scale factors that you want to use. So here we've used like 1 through 6 in steps of a half. Let's say you just want to use 1 through 5 or whatever it is, then this is how you would pass it into here. And this also selects the fit that you want to use. So here this is an exponential fit, or an exponential factory, as we call it, for like historical reasons. That doesn't matter. Okay, any questions about what I showed here? That's most of what I want to say about ZNE.
Nothing for me.
I actually am curious how the number of lambdas you use would scale. Is there any relation to like system size or precision? Like how, yeah.
The number of samples, did you say?
Yeah, exactly.
Yeah. Oh, great question. So yeah, so as you see, okay, this was averaged over different circuits, but you would see the same behavior with just one circuit. And actually, let me use this slide as an example, which better shows this. So here's just one circuit, and so we run one circuit, and that's the blue. This is the raw data, and you can see that because of the shot noise, meaning that at each one of these scale factors, the way you're computing this is you're repeatedly sampling output of a device, quantum computer, and you have to use some fixed number of samples. And so because of that, there's error bars on each of these results that you get here, and that also feeds into the to the fit. The looser the error bars are on the raw data, the looser the error bars are on the fit, and then correspondingly in the extrapolated value. So yes, so it is super important with CNE to use a let me say a reasonable number of samples. And what reasonable means, I couldn't define right now, but intuitively or qualitatively, you want the variance on these values, the blue ones, to be small enough so that your fit, makes sense and is not doing crazy things.
Okay, so it'd be fairly subjective to the particular device then.
I didn't catch the last part. Can you say again?
Sorry, so it's just very subjective to the particular device.
Yes, it is. It is
Okay.
very dependent on the device and other things too, but definitely on the device. Yeah.
One question that relates to this project, because kind of at the outset, we had this interesting kind of backwards problem for our benchmarking, right? So like normally when you benchmark the noise on a device, you're doing randomized benchmarking, which is effectively just swapping out a bunch of different circuits on the same device and trying to average over to get some information about how the device's noise behaves. But in our problem, we're trying to benchmark algorithms. And so one of the reasons we picked Penny Lane is because they market, their code is being able to kind of just swap out various hardware backends. Like you could try it on Rigetti, you could try it on IBM. But I guess my question is like, what are your thoughts on that approach, where you have an algorithm and you're trying to swap out different backends to try and do a similar like averaging?
Yeah, it's a great point. I think ultimately you're probably more benchmarking the device than the algorithm in this case, and that's more just a reflection on the state of the field, I suppose. If everything was perfect, then the algorithm should work the same on whatever device, unless I'm missing the point here. But yeah, I think the main thing that you'll see there is differences due to the different noise characteristics of the device. Is this sort of what you mean?
Yeah, I guess it's because benchmarking isn't my area. Is it then the case that you really can't benchmark an algorithm, and when you run it on a device, you're just seeing artifacts from the device's characteristics?
I think mostly, but I'm so like certain behaviors, I think you could benchmark in a sense. Let me see if I have an example of this. Yeah, I mean maybe just like the same example of the number of samples that you need. So yeah, I mean that shows up in like yeah, I mean each one of these algorithms and any variational algorithm really. And in some sense you're still characterizing the device there, because the readout errors are much worse on some devices than others, and so you would probably see that. But you could ask like for any variational algorithm, any of the ones here or others, like how many shots do I need to take in order so that the optimization landscape is well defined enough so that I can actually optimize. Because if it's jumping all over the place at every sample, then you're not giving yourself too much of a chance, or you're not giving the optimizer too much of a chance. So I think there's certain aspects of the algorithms like this that you could definitely benchmark. Yeah.
Okay. Yeah, thanks. We should maybe talk about that more outline.
Okay. Good. So okay, so the last thing on ZNE, and then I think we're pretty good on time. I can go through the last technique a little more quickly, and yeah, just to give you a sort of tutorial on that if you're interested. But the last thing on ZNE is, okay, how do I scale the noise now? So this is the last thing that I didn't say. So the original idea was the so-called pulse stretching. So this is the IBM paper that I mentioned by Kandala and others in 2018. And so they're thinking about like superconducting circuits, which boils down physically to pulses, microwave pulses that you send into the chip. And so those are the blue and the red things. And so if you look at this blue one, the blue ones are the 2 qubit gates and the red ones are the single qubit gates. So the key thing that matters for a pulse is its area. The area dictates the gate that you do. So if you do the same pulse for a lower amplitude, but for a longer time, so that it has the same area, you're in principle still doing the same gates, but under certain standard assumptions on the noise. This will have the effect of increasing it by the amount that you scale it by. And so that's the idea here. You could do it with 2 qubit gates, 2 qubit pulses, and single qubit pulses, and it's sort of the same thing. So that's pulse stretching or pulse scaling. And in Mitiq, since we wanted it, well, since usually, especially at the time we were developing it, you weren't writing pulses, you were writing gates. And also because we wanted to use it on different hardware, different backends, we wanted it to not be dependent on the pulses. And so we did a not novel by any means thing, but we gave it a nice name, I think, unitary folding. So here a gate or a set of gates, G, gets mapped to G inverse, which should be the identity if there's no noise, and then G again. So with no noise, yeah, it should be the same thing. But with noise, again, under certain standard assumptions, you can show that the number of times you do the G dagger, etc., the noise is proportional to that number. And so it could be a single gate, like I said, or it could be like the full circuit. And if it's the full circuit, so here's an example, Bell State circuit, Hadamard C naught. Then we take that, we do the copy of it. So that's the G, then we do the G dagger. So that's the inverse, and then the G again. Okay, and this is the technique that I referred to as global folding. So yeah, it's just our terminology. Global folding means that global is like the whole circuit, whereas local folding, local would be like 1 gate or 2 gates or something like this. Okay, so those are 2 ways to increase the noise, and there's many others. Like you can get creative with this. You can insert identities. You can insert instead of G dagger, it could be some other gates like I don't know, whatever your favorite letter is, and then your favorite letter dagger. So there's a lot of things that you could do here, but here's some of them. Okay, and here's an example of a variational algorithm, or the result of it at least, using error mitigation. So I wanted to include this, and then it's an example in the documentation. So I won't like go through the notebook now, but this exists. And so if you're interested or intrigued by this, then feel free to check out the code which produces this just on the Mitiq documentation online. So here, what are we doing? Okay, I didn't list the problem apparently, but it's VQE on molecular hydrogen. So you have 2 hydrogen atoms, and they're separated by some atomic distance, which is the horizontal axis here. So without any error mitigation, we see the following behavior with 0 noise. So this is the correct result. We're simulating a noise model. So we have full control over this. You see the blue curve here. So this is the sort of usual potential energy surface that you expect to see. And then as you increase the noise, and if I remember, I think it's just depolarizing noise to like 2%, then you see the orange curve. At 4%, it's the green curve, and 6%, it's the red curve, and so on. And so so now we've taken this and we've applied error mitigation, which I'm like 95% sure was zero noise extrapolation. It might have been something else, but it's something in Mitiq, at least I can say that. And here, you see a pretty nice thing that most of the curves are now overlapping, and they're overlapping at like the blue one, which was the zero noise. So that's good to see. The higher the noise is, the worse the error mitigation technique works. So that's not completely overlapping with the correct answer, but certainly better than in the unmitigated case.
Wait, sorry, did you say the higher, wait, is that red or, because I see like the orange and then oh no, that's the red, sorry.
Is it? Yeah.
Not the best color scheme. The highest one is the red, yeah.
Okay, and okay, because I thought like it was the 0.021 and then I was like, wait, but no, it's the 0.061.
This is the 6%, yeah.
Right.
So
Yeah,
the big
good-
takeaway
good
is
question.
that the mitigation is really giving you good results for a lot of different levels of noise. Or the unmitigated, you get shittier results the bigger the noise is.
Yeah, exactly. And that's quantified. So the relative error between the result that you get and the true result is here. So lower is better, right? Lower error. So the mitigated ones are sometimes like a factor of 10, 100 better than the unmitigated ones here. And yeah, as the noise increases, as you see here, the ratio gets worse. But you're still better in all cases. So that's good. If you weren't, there would be a problem. But this is just exemplifying that. Okay, very good. So the next one, yeah, I could go through it very quickly, but I think we only have like 5 minutes left. So I'm happy to call it here if we'd like and answer more questions, but up to you. What do you think?
Is PEC covered in the Mitiq kind of documentation? Like, are there examples using PEC? Okay, then I can just look at it later then.
Absolutely, yes. All of the things that I say here are written out with code examples in the documentation. Yeah.
Yeah, I'm really excited about this tool. Although I will say, so for the position, the point in time we are at with this project so far, we started maybe 5 or 6 weeks ago. Each student picked a paper, and at this point, just about everybody has an understanding of their algorithm and is in the coding phase. Some subset of my students have code that appears to be running the algorithm, but one barrier we haven't been able to break through is getting to reproduce the original results from the papers themselves, which I think is also, Indy's working on your linear system solver. I have a couple of other students who are stuck on those points. Just as a point to say that like this would be something I would really want us to be able to use, but we're not yet at the stage where our code is mature enough to be going to these noisy devices and using the error mitigation, because we're still struggling in the simulator.
Yeah, that makes sense. That's the first thing to solve. So yeah, in addition to like communicating what the software is, I also wanted to emphasize, maybe I could have done it more, but the principles of like that go into designing software like this, and also like the stuff that you're building. The one thing that I didn't mention, which is the most important thing, I would argue, and I don't know like everyone's background, but people from physics backgrounds don't really tend to do this. Computer science backgrounds, do it. But the most important thing is testing your code. So having really good, well-defined and small unit tests so that you can diagnose what's going on at each stage, because it's one thing to write 1,000 lines of code and then say, oh my God, it's not reproducing the result from the paper. That's so hard for anyone to debug and diagnose. But if you break this up to 5 steps, and step 1, you check, okay, I'm very confident that I know the circuit that I've designed is correct because I've defined these unit tests for it. And it could be on different numbers of qubits, etc. Or it could be for like if you have a molecule like you have here with molecular hydrogen, like am I computing the right energy in the noiseless case, so p equals 0, as a function of this atomic distance. So I can't emphasize enough, there's no problem with having more and more tests, other than it takes time, but it makes your life so much easier. So if there's one thing that I can encourage you to do, as you're working on these really cool things, is pick 3, 5, however many stages in your algorithm, and make sure that you're passing each of them independently and in a confident way that you do by defining unit tests.
Yeah, I really love this point. It's a point that so some of my students, when I'm trying to like talk through how to learn, like a lot of my students are in this stage of like, it's this is the first quantum algorithm that they've ever seen, and trying to talk through how do you get to the point where you understand how to code this little piece and then that little piece. Your point about unit tests is really important. Although part of the challenge for me managing these students is that I'm learning how to program VQAs basically at the same beginner level as my students. So having like that greater degree of expertise to help them, spot where it is that they're going wrong is a bit of a challenge for me. So perhaps.
Yeah, it's hard for anyone, like I said, to look at 1,000 lines of code and see why it's not reproducing the expected result. But if it's 20 lines of code that are not working, that's much easier to digest and try to get to a good solution. And so if each of your 20 lines are independent, which hopefully they should be if you're designing the code well, then you can diagnose each independently and really work in this sort of unit tested way.
This is a fabulous point, and maybe it's a good point just looking at the time that we can conclude on. I hope that, Ryan, you mentioned you had figured out Discord a couple of days ago, so hopefully you'll be available in the Discord. I'll make sure to connect students to you if you're available for questions. I know that my students would definitely benefit from your expertise, and maybe you mentioned you hadn't really talked about it here, and it was maybe the most important point about that unit testing. Maybe we can set up some time to talk about that too. These folks with their code in a more mature state.
Yeah, that all sounds great. Definitely.
Okay. Well, with that, let's thank Ryan again. Clapping with one hand over here. And I'm going to stop the recording.